So now you can see two diagrams down here on your left and on your right. So can you recognize what is in your left? So you can type your answers in the chat window, right? What do you see here on your left? If you are in the class, you need to answer me. Otherwise, no point of help. Yeah. So it's a hydrogen atom, right? So in fact, it is hydrogen atom, and we can even extend what you see is it's not H2, it's hydrogen atom. H2 is the hydrogen molecule, right? Okay, thank you. So in the hydrogen atom, so you have one proton which is represented in red and one electron rotating around it. So that is a very basic Bohr model for the atom. I think you all know, those who did chemistry, you know that it is not so that acceptable, but as long as it works, we can make use of that, right? And then on your right, what you see is helium. Now, interestingly, helium is a dis2, and so therefore you have two electrons and two protons. Those are in red. And what are the things in blue in helium? What are they? There are like two blue particles also. Yeah, some of you are giving me the answer. Those are the neutrons, right? So the two neutrons and two electrons and two protons. Now, when you think of the neutrons coulombically, that means when you consider the charge, those are not charged particles, those are neutral particles. So that is why we call neutrons. And electrons are negatively charged and protons are positively charged. And the charge of the electron we consider -1 and charge of the proton we consider +1. And in fact, for your additional knowledge, now these electrons we consider as a fundamental particles. That means you can't subdivide electrons as of now. To the science knowledge that we have, electrons you can't divide into subparticles. But protons and neutrons you can divide into subparticles. We call them quarks. So quark, right? So there are two types of quark called up quark and down quark. So up quark is charged 2/3 and down quark is charged -1/3. So for example, proton is made of 3 quarks. So the proton is not a fundamental particle. Why? Because you can have like even smaller particles called quarks. So proton is made of 3 quarks. They are called UUD, 2 up quarks and 1 down quark. So these are the charges of the quarks. So can you find the charge of the proton considering these up quarks and down quarks? So it has 2 up quarks and 1 down quark. Can you find the charge? Yeah, it's a +1, right? So you have 2/3 plus 2/3 minus 1/3. So this is +1 charge. And for neutron, it is UDD. So can you find the charge for the neutron? For the neutron, it is 0, right? So it's 2/3 plus -1/3 plus -1/3. It's 0. So these are like fundamental particles, sparks, but protons and neutrons are not fundamental particle. And electron, you can't subdivide even further. So electrons also considered as a fundamental particle. Okay. So those are like some background knowledge, good to know things. Now, interesting thing is that what can you say about the mass ratio, mass of electron to mass of proton? Can you tell me this ratio? Or mass of proton divided by mass of electron, what is the number? Yeah, so roughly it's 1,800. So this one is, sorry, 1,837, right? So just to be to make it easier, let's say it's 2,000 times. So mass of the proton is equal to 2,000 times. It's roughly equal to 2,000 times mass of electron, right? Now let's say you want to move. So from this hydrogen atom, you want to move either electron or proton. What is the easier to move? Is it electron or proton? Right. Most of you says it's electron. Yeah, everybody says it's electron that you can easily move. Can you explain what's the reason why electron is easier to move? Yeah, it's low mass, right? So electrons is lighter. So now let's say you have to throw something far away. So always lighter one is easier to throw far away compared to the heavier one, right? Yeah, good. Right, thank you. Right. So then we have a question here. What is electronics? Can anyone give me the answer for this one? Whatever you feel is acceptable here, but I need answers. So what is electronics? So you are doing a degree in electronics and automation, and someone asked, "Oh, what do you mean by electronics?" So can you give me the answer for that? Whatever you feel, you can write down as the answer, right? It's acceptable. You have 1 minute to do that.
Recording stopped.
Excuse me. It's your idea, right? So I don't need any correct answer. You put your idea in the chat window. What do you mean by electronics? Someone, someone asked this question. You don't need to Google and tell me. So you just write down whatever you think.
Recording in
Right,
progress.
thank you. So there are like a lot of interesting answers. So there are like philosophical answers also, and I don't need to see answers from the Google, right? So don't just copy and paste from Google or ChatGPT, right? So you just keep them with you. So I just ask you idea. Right. So I just copied this one from Wikipedia like a few years ago. So in Wikipedia, when I asked this question, what is electronic? So electronics is a branch of physics that studies the flow of electrons through various materials and devices. Right? It's kind of interesting. The key words here is that, so it's all about electrons. So electronics, electrons, right? So you see the similarity. And then flow of electrons through various materials and devices. So it's a study how to control those electrons or the how to control the flow of electrons through different materials and devices. So that is what we do. So when we are in the fundamental level, that we need to know this one. But when we move to the applied level, so we don't even consider this one, how it works. But it's all about the movement of electrons. Just keep in mind. Right. So now I'm moving towards another fundamental parameter. Uh, we call the resistivity. So this parameter resistivity, sometimes called specific electrical resistance, or we call it resistivity. Now remember that electrical systems and thermal systems, they are like kind of go side by side. So whenever you say resistivity or conductivity, there is a thermal conductivity and thermal resistivity, right? But in general, we are referring to electrical resistivity always. So the electrical resistivity is a property of the material. So we represent that with rho. And if you want to get the relationship, like let's say we have a block of material where you have cross-section area is A and length is L. For that, if you want to know the resistance you can write rho L over A. So basically, this is the resistivity and this is the resistance. Resistivity and resistance. And the longer it is, the more resistance you have. The thicker it is, the less resistance you have. So when this one goes up, resistance goes down, right? So this is simple relationship. However, remember that this parameter rho is some sort of characteristic to the material. It depends on the material. So different materials have different rho values or the resistivity values. So now, depending on the resistivity value at the room temperature, we differentiate generally, right? So this is generally we differentiate our materials into three different groups by considering the resistivity of the material, right? So we have insulators, semiconductors, and conductors. In fact, apart from that, we have superconductors as well. So I'll come to that shortly. So now insulators, where its resistivity is higher than 10 to the power 5 ohm centimeter. So those are the units. So if the resistivity is higher than 10 to the power 5, we consider them as dielectrics. So dielectric is a different name for the insulators. So then things with resistivity in between 10 to the power minus 3 and 10 to the power 5, we consider them as semiconductors. And then we have conductors where its resistivity is extremely small, that is less than 10 to the power minus 3. Then we have superconductors, their resistivity is more or less 0. Right? So there are certain places where we use superconductors, so I'll come to that shortly. Now, there are few things that you, so these numbers you don't need to remember, right? So I don't ask for the exam or anything. These numbers I don't want you to remember, but just in case, good to know certain numbers, right? Roughly to get the idea. Now there are kind of very interesting properties associated with the resistivity. Now, one thing is the temperature. Temperature is a very interesting property that any thing can have. Now, in case of insulator, so let's say this is my temperature, my x-axis, and y-axis is resistivity, rho, right? So in case of insulators, resistivity is very high, right? So resistivity is very high. And as you increase the temperature, what happens is that its resistivity is decreasing. Right? So that's a property. Then in case of semiconductors, resistivity is slightly lower than that. For the semiconductor also, when you increase the temperature, resistivity is decreasing. This is conductors, sorry, insulators. This is for the conductors, semiconductors. And in case of conductors, resistivity is very small. However, when you are increasing the temperature, what happens is that its resistivity is kind of increasing. So this is interesting graph to remember. So now one thing that you should know is that how to explain this behavior considering the situation of the electronic system. So we'll take a look at that shortly. Now, again, we are moving towards the atomic structure of the material. Now here you can see two different atoms. We have silicon and germanium. So if you look at the periodic table, both silicon and germanium coming from the fourth group, that is the fourth column in the periodic table. So you can recognize that when you look at the outermost shell here, we have only 4 electrons. So in the germanium also, we have only 4 electrons. However, when you look at silicon, you have only 3 shells. For germanium, you have 4 shells. So that's one of the differences that we have. Now this outermost shell, so in this case, this shell, and in this case, this shell, we call it valence shell. Right? So this we call it valence shell. The electrons in the outermost shell, we call them valence electron, right? So this term, get familiarized with that. The electrons in the outermost shell, we call valence electron. The outermost shell is called valence shell. And also energy, which is required to remove electron from valence shell to make it free electron, that is also called a valence, right? The term valence is used to indicate the potential. Potential is the energy required to remove any of those valence electrons. So the potential required to remove valence electrons, we call it valence. Then outermost shell is also called valence shell. And the electron in the outermost shell, we call valence electron, right? So just remember those things. And interestingly, these shells, although like this looks like a physical arrangement, the energy of the electrons in those shells are getting higher. So innermost shell has the lowest energy, and the next shell electrons have a little bit higher energy, and the electrons in the valence shell, they have the highest energy in this atomic system. Is it clear? Right. So you can click yes and no. Is it clear, my explanation here? So if it is not, you can click no, right? Okay, thank you. So let me repeat it. The outermost shell, we call it valence shell. The electron in the outermost shell we call valence electron, and the energy that requires to remove electron from the outermost shell, that is called valence. And when you consider the energy, valence electron has the highest energy in the atom. So those are the things that you take from here. Right. Then a few more definitions. So after that, I guarantee that we will move towards something else. Right? So there are like few definitions. One is isolated atom. So the term isolated atom, what it represented is so atom which is like not influenced by any other atom, which is like one single atom. In general, we can't find isolated atom, right? Generally, like so, even in space, if there are atoms, so they are like there are few atoms close by. So usually, practically, we don't see isolated atom. But if we have an isolated atom, electrons in each orbit have defined energy associated with that, right? I'll come to that shortly. I'll explain it again, right? In case of solid, now remember uh, uh, we have like three phases in material. We have solid phase, liquid phase, and gas phase, right? So those are the three main phases that we have. Now let's consider water. So when you have ice, those water molecules are packed very close by. So in case of liquid water, water molecules are a little bit far away. In case of gaseous form, so this is the container, molecules are even far apart. So when it comes to solid system, those atoms or the molecules are like packed very close by. So in that case, we don't have isolated atoms for sure, right? So when you have solids, you don't have isolated atoms anymore because they are packed very close by. So in that case, energy levels of the outermost orbit electrons are affected by the neighboring mass. So I'll explain that also. Then, so the electron in the same orbit exhibits different energy levels. So although they are in the valence shell, different electrons have different energy levels. However, the electrons which are in the inner orbits, they are not affected by the presence of neighboring atoms. So that is what we call band theory of solid, right? So in the band theory, we consider isolated atoms and atoms packed close by. So in isolated atoms, we have very sharply defined energy levels. In solid, those are not the case. The atoms are packed very close by. So in that case, outermost shells, we have different energy levels. However, the innermost shells, they are not affected by this one, right? So let's discuss this a little bit in detail. Right. Now, what you see here is energy diagram, right? So this is an energy diagram. Here what you see is the nucleus, right? So nucleus is at the center and in the radial direction, right? So the radial direction is that you have the center here, you are going outwards. So this direction is a radial direction. This direction is also radial direction. This direction is also radial direction, right? So this diagram, things are represented in radial direction. Now remember, although this looks like a physical one, so the physical location of these ones are basically represented in the angles, right? So this one here, and it goes all around, right? So this is roughly 1/4 of the atom is represented here. Now, the energy is basically close to the nucleus, where you have the lowest energy. And this band, so you can see that this line, it has very sharp energy. Is it clear? this line, you have some sharp energy level, right? So it's the equal distance. Is it clear to you? Can you click yes and no? Right, thank you, right? So remember that. So why do we have this line? That means energy of these inner electrons are the same, right? They are very well defined. Energy of these inner electrons in the inner shells are the same. Very well defined. It's a line. However, now, so this one basically it looks like you have one inner shell, and what is this shell? The outermost one. How do we call it? It's the valence shell, right? So outermost shell. Now, if you look at it, the representation is kind of different, right? So let me go back to the previous diagram. Now here, the outermost shell is kind of one single line, right? So these are like representation of isolated atoms. So when you have isolated atom, we have very sharply defined energy level. So energy of these valence electrons are the same. However, here what we have is uh, energy levels. The outermost shell is affected from the presence of neighboring atoms. So that the outermost shell, it can have either this energy or this energy. Right? So this innermost shell, you can have only this energy. It's precisely defined. But outermost shell, you can have this energy or this energy. It's split into two. So this is a case where energy levels are split into two. Now let me label these electrons. A, B, C, D. Can you tell me what are the electrons having higher energy level and what are the electrons having low energy? Can you write down electrons with higher energies here? Sorry, I'll label this as the E and F. Sorry. All right, thank you. Right. So some of you say it is E and F, and some of you say B and C, and some of you say it is A and D. Now let's take a look at. Now, what is the energy at this point? When you look at this one, what is the energy at this point? It is zero, right? So according to this diagram, energy is zero, and as you go in the radial direction, energy is increasing. Let's say the energy of this one is P1. And if you say energy at this point is P2, P2 energy is higher than P1, right? So definitely energies of these electrons are smaller compared to any other electrons in this system. Is it clear to everyone? Right. So because energy is increasing as you go in the radial direction. Right. Okay, good. Right. So that this answer is not acceptable. Those who are giving. So these are the ones having lowest energy level and their energies are fixed. Right. So then the valence band, we have two splittings here. So this one has a lower energy level and this one has a higher energy level. So the A and D, they have the highest energy levels, and B and C, they have little bit lower energy level. Is it clear? Right, right. Thank you. So now when you look at this diagram, so inner shells, they are not affected by the neighboring ones. The valence shell, outer shell is affected. Now in this case, the splitting is 2. You can have splitting of many numbers, right? So as long as you have like different levels, you can have. So what the interesting thing is that this electron has higher energy compared to this one. So therefore, now no longer this is a shell, this is a band. So electron could be in this level or this level. So this is what we call valence band now, because it's not just single energy, it's a band. So we call it valence band. Right. Now, since you have energy, so sorry. Right. So now you have some energy level here, some energy here, some energy here, and as you go up, there is a some energy level. That is what we call conduction band. It is not a shell. So here you have shell. Actually, this is not a physical representation. You can see that these are the energy levels, right? Although it's like a real representation as well, because these electrons are like very close to the nucleus. Shell 1, shell 2 is far away, right? So it's kind of a physical representation as well, but in physical representation, you don't see electrons in two different levels, right? So they are in the same level, but energies are different. And there's another energy level, which is little bit higher. So this is called valence band. So the electron in the valence band, they are attached to the nucleus, right? So they are not free electrons, so you can't move them. Electrons in the inner shells, they are very well attached to the nucleus. You can't move them at all. However, if you supply a little bit of energy to this electron, and if you could move them to a little bit higher energy level called conduction band, in that case, those electrons we call free electrons. Those are the electrons we can freely move here and there. So electrons in the valence band or any of the inner shells, those are attached to the nucleus. We don't call them free electrons. Those we can't move them. The electrons that we can move are in the conduction band. Right? Those are not, there's no attachment to the nucleus. They are having the highest energy. Is it clear? Any question to ask? Request to explain conduction band. Right? I'll draw this diagram again here. So this is my nucleus. Right? This is my nucleus, and then my energy diagram. Okay, nice to draw. These are my energy levels, right? So as I go up, my energy levels are increasing. Then I have my first one, shell 1, that goes here. There are some electrons in the shell 1. These are electrons. And then outermost one, the valence band. So the energy levels are splitted. So some of the electrons are in higher level and some of them are in lower level. So this is energy. Then there is another energy level. If you could provide little bit of energy to these electrons, we can move to another energy level. So this is inner shell. This is valence band. So these are energies of the valence electrons, right? And then these electrons, by supplying little bit of energy, you can move them to a different band called conduction band. What is this energy called? Any idea? That is the valence, right? This is called valence energy. The electron to move from valence band to the conduction band, electron in the valence shell, that valence electron, if you want to move from valence band to the conduction band, this energy is called valence, right? So this energy difference is called valence. If we supply valence of energy, we can move them to conduction band. So conduction band is little bit higher. It's not a shell. it's a different energy level, right? So here we represent shells as well. However, so this one is the energy diagram. Now is it clear? Right. So next slide onwards, I'm not drawing this as atom. This is just a representation. So these ones, I will represent it like this. Energies, I will represent like this. So lowest energy level, this energy level, this one. Because there's no meaning of having radial one when it move to the conduction band, right? Okay, great. Right. Now you can see energy levels. Here you can see three different materials for the insulators, semiconductors, and conductors. How the valence band and conduction bands are behaved. So there are like a lot of energy levels down here, but valence energy level is just represented here. Now valence band is here for the insulators, and conduction band is far above it. So this difference is very large, and if you want to move electron in the valence band, so energy, so this is where the electrons with the highest energy. So you want to move it here at least, right? So this is what this energy difference is what we call the valence, the energy required to remove electrons from this one to this one, right? And when it comes to semiconductors, this energy difference is less. Right? So we call this band gap. Right? So it's a valence band and conduction band. So this is what we call the band gap. Now, interestingly, when it comes to conductors, at the room temperature, this one is the valence band. Right? And let me use different color blue. This is our conduction band. What is mean by this? Now, at room temperature, we don't have any electron in conduction band for the insulator. In semiconductors, we might have few electrons jump to there. However, here this is overlap. That means even in the room temperature, there are a lot of electrons in the conduction. Some of the electrons in the valence band, they are already in the conduction band. So that means they are basically belongs to the conduction band, and those are free electrons. So you can understand now, for the conductors, we have a lot of free electrons available. For semiconductors, you don't have a lot of free electrons. And insulators, you don't have any electron in the conduction band. So the higher the number of electrons in the conduction band, the more you can move here and there, so that the resistivity is decreased. Right? So the same one with a different representation here. Right. So the band gap, I'll explain it. So you can see the same diagram here, but with little bit of more information. Now, this is the valence band, right, for the insulators. This is the valence band for semiconductors, and for conductors, this valence band and the conduction band, they are overlap. Right? So it's overlap basically. Some of the electrons are readily in this one. Now, this energy difference. So this is what we call the band gap. So this band gap is very large, and it is measured with the electron volts. So it is larger than 5 electron volts in most of the cases when you consider insulators. When you consider semiconductors, for example, silicon, band gap is 1.1. For germanium, it's 0.67. And gallium arsenide, so like those are like composite materials, it's 1.4. Right? So this band gap is kind of small compared to this 5 electron volts. And in case of conductors, you don't have band gap. Right? Okay. Now, question arises. So these numbers you don't need to remember, right? Those are just giving you some idea. Now let's say how do we move one of these? Now, when you look at this one in conduction band, for the insulators, you don't see any electrons, right? But in case of semiconductors, you can see few electrons in the conduction band. In conductors, you have a lot of electrons in the conduction band, right? So now the question is, if I were to move one of these electrons to the conduction band, what should I do? Any idea? You can write your answers in the chat window. Any idea is accepted. Supply energy by heating. Okay. Supply energy. Somehow we need to supply energy, right? Okay. Now let's see. Okay, let me ask this question. What is temperature? Any idea? Heat, okay. Flow of heat. The measurement of heat. Temperature is velocity term. Flow of heat, okay. All right. All right. So let me show you this slide. Right. So we all know this equation, right? So ideal gas equation, PV equals nRT. Click yes and no. Do you know this equation? PV equals nRT. All right. Okay. Most of you know, few of you don't know. So it's pressure, volume. N is number of moles that you have, and R is a constant, and T is the absolute temperature, right? So this is if you have some sort of air in a closed volume. So if you have a number of moles at a temperature, so this equation represents how the pressure, volume, and the temperature vary. Give me a second.
Recording stopped. Recording in progress.
So if you have like a volume, V volume, the pressure is P, and at the temperature T. So this one basically represents how those are related, right? Now also, if you remember kinetic theory, Kalakawade, so there's another equation called PV, that is also pressure and volume equals 1/3 of mn c squared bar, right? So those who remember it, what is m here? Can someone remember this? Yeah, it's mass, of course. It's a mass of one single molecule, right? So it's a mass of one single molecule, right? Thank you. Then N is number of molecules, right? So the simple N is number of moles. So this is number of molecules. So it's basically N divided by Na is simple N. What is Na? It's called Avogadro number, right? So it's a number of molecules in a mole. Right, so this N is number of moles. Okay. Right. Okay. Thank you. Right. So then, what is C here? It's not velocity of light, right? Okay, so usually we use C for the velocity of light, but here C is representing velocity of the molecule. And what happens is that when you have a system, the molecules are moving in random directions, right? With different velocities, V1, V2, V3, V4. So C squared bar is basically C squared bar is basically you take all these velocity V1, you square it, plus V2, you square it, V3, you square it, V4, you square it, right? So assuming that there are only 4 molecules, you sum it up, then you take the average, you divide it by 4. Right? So this is what we call root mean square, right? Sorry, mean square, sorry, not root. Right. So this is not the square root. So it's the squared, you sum them up and divided by number of molecules. Okay. Right. So it's the same PV in both the equations. However, the other side is different, right? So you can just equate those two equations, PV equals nRT and PV equals 1/3 mn c squared bar. Right. So then you can just move items here and there. So I just introduce half here. And that half is here. And 1/3 is readily there. So just move items here and there. So do you want me to work this out? Maybe I'll work this out. That may be much easier. So I'll take this one, right? It's nRT equals 1/3 n c squared bar. Now I will multiply. I'll take nr. I'll divide everything with 2. I'll take this 3 top, right? So then you don't have this one. I have 3. Then I'll divide everything with 2. So I have, okay, so m is missing, right? So this m, I missed it, I'll put it here. So now what I have is 2 divided 2 into r into n. N, if you want, I can rewrite as n, that is capital N divided by Na, right? So this is number of molecules divided by number of molecules required for 1 mole. So that is the number of mole, right? Into T. So this is N and this is Rn. You have T here. Equals n c squared bar. Now I can cancel this out, this n and this n, if you want, right? Then what I have here is 3 divided by 2 into R divided by Na into T is equal, I'll write this one in this direction, half m c squared bar, right? So what is this R? Is it a constant or not? Say yes if it is constant, say no if it is, it's a constant, right? It's a universal gas constant. Na is the Avogadro number, that is also constant. So 3 is a constant, 2 is a constant. So all together these are constants, right? So you can write that mc squared bar equals some constant. I will put k into t. Right? Then what is this? half mc squared. It's the kinetic energy of one molecule, right? So it's a, you remember its kinetic energy is basically half mv squared, right? So instead of v squared, we have average square velocity. So it's basically, this is m is the molecular mass. So what you represent here is that half m v squared. So v squared is taken average. So it's basically the kinetic energy of a molecule. Right? So it's the average kinetic energy of the molecule. So it's average kinetic energy of a molecule is equal to k into t. So if you have something like y equals k into the x, we can write y is directly proportional to x, right? Is it clear? So if I use the same, I can say this is directly proportional to t. Right? Now, when you look at this equation, what it says is that in case of gases, temperature is directly proportional to the average kinetic energy of the molecule. Is it clear? Yes or no? So it's the average kinetic. So in other words, what it says is higher the temperature, the more kinetic energy you have. In other words, you can interpret this as in words, temperature is a measure of average kinetic energy of molecule, right? So since these particles are moving in different random directions, usually we call temperature is a measure of random kinetic energy in a system. The term random come to the picture is that they are moving in different directions. So when someone asks the question now, what is temperature? You can always say it's a measure of random kinetic energy of the molecule in a system. Although we proved this one for the uh, gases, this is true for solids and liquids as well. Right? So if you want to prove it, you need to have different approach. So since things that you know, I just use it to prove it, right? So remember that whenever someone asks the temperature, so that's a measure of random kinetic energy in the system, right? Now, if we increase the temperature of the system, what happens is that the whole system start increasing its energy. So that energy of the electron also increase. So electrons with higher energies, they will jump to the conduction band if that energy is high enough as the valence energy, right? So that is how you move electrons in conduction valence band to the conduction band. Is it clear? Right. Yeah, when you heat it up, you are providing more kinetic energy to the electrons as well as whole system. So when you have high energy in the electrons, they will jump to the conduction band. Right? Okay. Now I have, so if you remember the graph again, so this is my x-axis is temperature and y-axis is resistivity and x-axis is temperature. So in case of insulators, it's like this. In case of semiconductors, that is also decreasing. In case of conductors, its resistance is increasing. So this is insulators, this is semiconductors, this is conductors. Right? When you increase the temperature, this is what happens to the resistivity. Right. So can you explain why the resistivity is decreasing for insulators? When you increase the temperature, why resistivity is decreasing? Any idea? resistance. Right. Okay. Right. There are few answers, so let me explain this one now. When you heat this up, so that means when you increase the temperature, what happened to the energy of these electrons? Will it increase or decrease? That will increase, right? Although this representation is not that nice, so then let me draw some electrons in different color. So let's say there's a one electron here, another one here, another one here, another one here, another two here, right? And the electrons with the red one also there. Now let's say if we increase the temperature, what happens is that the energy is increasing, right? So energy is increasing. Now if you want to move this, now when you increase the temperature, basically all the electrons are receiving same amount of kinetic energy roughly, right? Now what happens is that if that energy given by increasing the temperature is like large enough, like 5 electron volts, what happens is that the electrons having highest energy. So these two electrons are the electrons which are having highest energy. They will jump to the conduction band. Is it clear? Right. Right. So then what? So two electrons jump to the conduction band, so that you can see that its resistivity is slightly decreased because you have few electrons in the conduction band. Now, if you increase temperature further, now we are at this temperature. If you increase temperature further, then electrons with little bit higher energy levels, like the red ones here, those electrons will jump to the conduction band. Then you have little bit more. So at this temperature, you have more electrons, so that resistivity is even decreased. And if you try to increase temperature further, you will get these electrons also jump to the conduction band, so that you have more electrons at this temperature, so that your resistivity will decrease further. Is it clear? Right? So as you increase the temperature, because different electrons in the valence band, they are having different energy. So by increasing temperature, you are providing almost same energy to the system. However, electrons having highest energy, they will jump first. For certain electrons to jump to the conduction band, you need to have higher and higher temperature. So this is what happens as you increase the temperature. You will have more electrons in the conduction band and they will do the conduction, right? So in case of semiconductor, that is also the same, right? The same explanation you can give. So the higher the temperature, the more electrons will come to the conduction band and you will get less resistivity in the system. Right. Now we have a kind of strange behavior for the conductors. The reason is that in case of conductors, you have a lot of electrons in the system. Right? Now, when you increase the temperature, what happened to the kinetic energy of those electrons? Will that be increased or decreased? Kinetic energy will increase. That means these fellows, they are start moving here and there really fast. Right? Now, let's say we have a conductor. So this is a copper cable. So these are like free electrons that are in the system. Right? Now, when you apply electric field, say we apply electric field, these electrons will start moving in this direction. Right? So what do you mean by current? current is number of electrons moving, right? So now if you consider this cross section, number of electrons moving through this cross section is what is called current. So it's dq over dt, in other words, right? So the higher the voltage, the more electrons will move, right? So because electric field is in this direction, electrons are negatively charged. So therefore they will be moving towards in the opposite direction. So that is how you get the current. So the higher the voltage, the more electron will move in this direction, you get more current. Now, what happens is that if you increase the temperature, by default, these electrons, they are starting moving in random direction, here and there. Is it clear? Yes. Now, when you apply electric field, we need to move, for example, this electron, it's moving in this direction, and we apply electric field, that is a force in this direction, we need to move it here. So therefore, it's basically the movement is disturbed. And also, because of this highly movement of here and there, they go here and there and collide with each other so that it disturbs the flow. Now, this is like, now, for example, in case of semiconductor or insulator, it's like you have a expressway, there are only few vehicles. Right? So vehicles are like electrons. So the number of vehicles passed through the gate is called the current. So if you have more vehicles, they can transport more people, right? So let's say the transporting people is the purpose. However, if you have more than enough vehicles here, it's like in conduction band. Now, if these are like having kinetic energy, what happens is that these fellows will go and hit in the different vehicles and disturb the transportation. So therefore, now in case of conductors, when you increase the temperature, what happens is that collision will increase. As a result of that, it will stop or the disturb electron methodical movement. So that as the temperature increases, the collision will increase so that the resistivity will increase in case of conductor. So is it clear? Now, let's say if you want to make a superconductor, that means disturbance should be minimal, right? So what we do is we take a conductor like this and we cool it down to minus 270 degrees Celsius. Now what happens when you cool it down, since it is conductor, you already have electrons in the conduction band, right? When you cool it down, what happens is that their kinetic energy is removed. Now, wherever you apply electric field, they will move freely so that collision is minimized, right? So that is how you achieve superconductivity in most of the machines like MRI machines. It requires large electromagnet so that the resistivity should be minimal. So therefore, they run separate cooling plant with liquid nitrogen and cool it down to absolute zero so that there's no effect from the temperature. Right? Is it clear? Right. Okay. Thank you. Right. So this is all about what happens to the materials when you change the temperature. So you should be able to explain these things if these are in the exams, right? So clearly with your logic, you should be able to explain these things. Right. Now we are moving towards, in general, semiconductors, right? Now, before moving toward this one, now we have three different materials: insulators, semiconductors, and conductors. So for us to do electronics, to make electronic devices, what are the important material? Are they insulators, semiconductors, or conductors? Okay, thank you. So generally, in general, answer is semiconductors. However, that is not the case, because now let's say we have silicon substrate, right? So this is silicon substrate. Now let's say we have PCB. So this is copper clad one. So you have some copper tracks, right? Connecting different devices. So these are copper tracks. Then in between, you need to have insulation. So in between, you should have to have insulation. So without having insulation, all the circuits will be short circuited. Right? So therefore, in case of electronics, we need insulators, semiconductors, and conductors. Right? So the requirement of semiconductors we'll discuss later on. So that is to make the device, you need to have semiconductors. Most of the electronic fundamental devices are made out of semiconductors. However, you need conductors to move electrons to that area, and you need insulators to isolate the tracks. Right? Is it clear? Now, this is a silicon atom, right? When you consider silicon, so this is the innermost shell, then the next innermost shell, and this is the valence shell. In the valence shell, you have 4 electrons in silicon. Now, remember that for all these electrons, the corresponding proton is inside, right? So now, for example, here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 electrons outer shell, and there are 14 protons inside. So that when you consider this atom, it is neutral, because the positive charges and negative charges are equal numbers we have in the system. Now, in general, when you have silicon, if you have another atom close by, it make this kind of bond we call covalent bond, sahasanjudha bandha, right? So they share these electrons, and generally what silicon does is not only this, it makes covalent shell with 4 different, now for example this one, it makes 4 covalent bonds with 4 neighboring atoms. So that is how they stay in the lattice, right? Now this slide onwards, I'm going to forget about the innermost one, because they are not moving or anything happens to that. So therefore, I'm going to forget about the innermost shell. I'm only going to consider the outermost shell. Right. So again, this is the 4th group. You have carbon, silicon, and germanium. Right. So this is silicon. And here what we have is the outermost shell is represented. So the outermost shell, electrons in the outermost shell is represented here. Now these lines, they are representing covalent bonds. Now, when you look at this one, this electron could be coming from this silicon, and this electron could be coming from this silicon. So basically, because of this covalent bond, these 2 electrons are shared with both. So this one also the same, this one also the same, right? So this is like a infinitely large one. So I have not drawn these ones, right? So it's like extended to every direction. So when you look at the atom like this, it has 8 electrons in the outermost shell. Basically, outermost shell is filled so that it is kind of stable. Now, when the temperatures near absolute zero, what is the property of the kinetic energy of the system when you are about to reach absolute zero? What can you say about the kinetic energy? Absolute zero is 0 Kelvin, right? There's no kinetic energy. So basically, when there's no kinetic energy, all these shells are connected. So the valence electrons are there, and you don't see any free electrons in the system. So all these electrons are belong to this covalent bond now. So no free electrons in the system when you add absolute zero. So when you add absolute zero, silicon crystal is an insulator. There's no any semiconducting property when you add absolute zero. Is it clear to everyone? Right. Now let's see what. So this is the situation where you have the absolute zero. Now you remember that although we have 2 electrons here or 8 electrons here, not all the electrons in the valence band having the same energy, right? Because you have the effect from the neighboring atom. So different electrons are in different energy level. Now, if the temperature is slightly increased, electrons with higher energy, they might jump to the valence band, sorry, conduction band, right? Now, let me clearly explain this one. So in this diagram, what we represent is these are the bonds, and we are representing only outermost electron, right? So they are in the bond. So absolute zero, everything is in the bond. There's no, it's like no free electrons at all. Now, when you increase the temperature, if you increase the temperature, this is what happens. Electrons with the highest energy in the valence band, they will jump to the conduction band. Now, for example, this electron, it jumped to the conduction band. So that it's no longer belong to this covalent bond or the valence band of any of the silicon atoms. So that this is a free guy, you can move here and there. But this electron is not a free guy. This electron is not a free guy. This electron is not a free guy, you can't move them, but this electron you can move here and there. Now, what happens is that once you remove this electron from the system, you get some requirement of electron, a hole. We call it a hole. Hole is a kind of virtual place where it requires an electron. So we consider hole as a particle, but it's a virtual particle. We call it a positive particle. So I'll show you how hole is moved. Now remember that by increasing the temperature, whenever you are creating an electron, free electron, at the same time you are making a free hole as well. Right? So we call that electron hole pair is created. So whenever you are creating free electron because of the temperature, automatically you are creating free hole as well. Is it clear? Right. So when you have pure material like silicon, whenever you create free electron, at the same time you are creating free hole. So basically number of holes and number of electrons are the same. Now let's see. So electrons, of course, you can see they are free. You can move them here and there. Let's see how holes are moving. This is the same slide. Okay. All right. So this is slightly different slide. I will explain why this is. So let's say we have a hole here. It's a vacancy, right? Now, whenever there is a vacancy, what happens is that the neighboring electrons, which are having little bit higher energy, try to get involved in that hole, right? So this is a hole, and the neighboring electrons, this one and this one, probably this one and this one, they are interested in whoever having higher energy. What happens is that this, for example, if this one is having higher energy, this will jump here, right? So if that electron jumps here, this is what happens, right? So this electron jumps here. Now it's like, although the electron is jumping, so this electron, is it a free electron? Yes or no? It's not a free electron, right? So this one belongs to a bond, but since there is a vacancy, this guy is interested in that vacancy and try to jump there. So if this one jumps here, what happens is that hole is created here. Now it's like, although negative charge is moved in this direction, it's like positive charge is moved in the other direction. Both are the same, right? moving negative charge towards this direction is exactly equal to moving the same positive charge in this direction. So therefore, so when you move this electron here, basically we call it moving of hole. Now what happens is that the hole which was originally here, it moved here. Now this electron is interested in this fellow. So probably with a little bit of electric field, this electron might jump here so that you can move hole further. Likewise, right? So likewise, you can move hole here and there. It's basically the requirement of electron is moving so that we can call it a positive charge particle called hole is moving here and there, right? Right. Now, when you look at this one, we are getting very small number of electrons in the system so that the conductivity is not good enough for our work. If you take pure material, we call intrinsic material. Pure silicon is intrinsic material. So that what we do is we add impurities, right? When you add impurities, we call it process. We call it doping. So we have pure material, we add impurities. That means different materials are added. This is what we call doping, right? So once you dope, once you add the impurities, you can see a lot of interesting properties comes up, right? Even for a person, when you add alcohol, you see like when you add impurities like alcohol, you can see different interesting properties. The same thing happens to the semiconductors also. Now, semiconductor doping is not just like human beings. It's a well-controlled process, right? Doping is the process of adding very small, well-controlled amount of impurities, right? So well-controlled. So we are the one deciding how much impurities are added, and it's a very sophisticated system in the material science. They control it. Right. So by doping, you can increase and decrease the resistivity. I will explain how do we do that. So in case of silicon or germanium, we can get it from column 3 or 5 of the periodic table, right? Now, if we consider column 5, so in the outermost shell now, arsenic is coming from column 5. The outermost shell, you have 5 electrons. And for the silicon, for the outermost shell, you have 4 electrons. Now, if you take a silicon lattice and you replace, so for example, this silicon atom is replaced with arsenic atom. Now, what happens is that it will make 4 covalent bonds. Right? It will make 4 covalent bonds. However, there is additional electron. It's not bonded to any of those neighboring atoms. So this electron works as a free electron or the extra electron to the system. So now what happens is that in the silicon lattice, you can have thermal hole electron pairs plus additional electrons coming because of this doping. So these electrons act as free electrons in the system. Right? Now, however, one thing that you need to understanding is that now for this silicon, you have, sorry, arsenic, you have 2 here, the 8 here. So it's 2 and 8, 10, and 5 in the outermost shell. You have 15 electrons in the system. And also you have 15 protons also in the nucleus. So if you consider this atom itself, it's neutral. And if you consider this as a whole, it's neutral. However, you are getting extra free electron here. When this free electron is gone, this becomes positive ion. Is it clear? Right, thank you. Now, this is the free electron. So here again, we are representing only the outermost shell, and +4, that is the valence in semiconductors like silicon. And then we have +5. So we have 5 protons in the nucleus and 5 electrons in the valence band, right? So these are like corresponding electrons are represented, protons and electrons are represented, right? So silicon, we know that we have 14 protons inside. This 4 is corresponding to these 4 electrons. So that is how they are neutral. So here, in case of arsenic, you have 5 electrons plus this, and we have 5 protons corresponding to that. So that is why this is neutral. Similarly, you can go with column 3, where you have only 3 electrons in the valence shell. You can dope silicon with that, for example, boron. So this is a boron, and you make 3 bonds, and then there's no electron to make a bond here. So that is a requirement of electron. In other words, it's a free hole. So any of the electrons in neighboring atom could jump here and make the covalent bond here. So when you add impurities from column 3, we call acceptor impurities. That means they are ready to accept electrons. And when you add impurities from 5th group, we call donor impurities. They would like to donate electrons to the system. Right. Now, this is what I have shown previously. Now here you can see boron, right? So when you have boron, there is a vacancy. Vacancy means it's a free hole. Now the neighboring electrons are interested in jump here, and they're simply moving the hole here and there, right? So you can move this one. Now, concluding what we discussed today, if you have pure material like silicon, we call intrinsimic material. So in that case, number of free electrons is exactly equal to number of free holes that we have, right? So here P and N, they are representing electrons and free electrons and free holes, right? So this is pure material. And in case of material that are having large number of N's compared to P's, so that is if you dope with donor material, like from the 5th group, so free electrons is higher than free holes. So in that case, we call it N-type material. If it is other way around, we call it P-type material. Now, in case of N-type material, electrons, free electrons are called majority carriers, and holes are called minority carriers because they have the less number of population. But in case of P-type material, holes are the majority carriers, and electrons, free electrons, are the minority carriers. Hope it is clear. Right. Yeah, this slide, there's nothing interesting. Now, these are like some terminology. We discussed what donor is, what acceptor is, N-type material, P-type material, majority carriers, minority carriers, intrinsic semiconductor. Those are pure semiconductors where you have number of protons, number of free holes, and number of free electrons, they are the same. Then we discuss eccentric materials. We didn't use exactly this word, but it's a dope semiconductors. In that case, either N or P, they are not equal. Either N or P is larger. Depending on that, you have majority carriers, either P or N. Last few slides. So initially, germanium was the material that people widely used to make semiconductor devices, but there are a lot of issues associated with that. Then silicon came into the picture, and silicon has really interesting properties. We'll come to that in a slide. And then we know that germanium and silicon are widely used. Carbon is also coming from the same group. But why don't we use carbon? So whatever the material that we always use its crystalline form. Right? So carbon stays in different forms. So the crystalline form of the carbon is what we call diamond. And you know the answer, diamonds are very expensive. And the packing fraction is very high. So therefore, diamond is not really a semiconductor. So it's like a insulator. And yeah, there are certain applications where you use diamond as semiconductors, but the temperatures has to be very high, like 400 degrees Celsius. Now, suppose you are making a satellite which grows close to the sun. When you have electronics made with silicon, when you are reaching to temperatures like 400 degrees, they are more or less conductors. They don't have semiconducting properties. So in that case, probably you can use diamond. Other than that, carbon is not really used as a semiconducting material because the crystalline form of carbon is diamond, which is very expensive, and also it is not that clean. It's like kind of contaminated with different other things, and also it's very difficult to make it happen. Right. So this is a comparison of all three materials. Carbon very expensive, and in diamond form, band gap is very large, like 6 electron volts. So if you remember the number, anything bigger than 5 is kind of insulator. Then silicon is very cheap, and you can get very high purity. And also, when you have silicon, you can make it's a semiconductor, but if you want to make insulator, you can just oxidize it. So silicon dioxide, it's a very good insulator. That's another advantage. I'll discuss this next week onwards. And then germanium, it has high mobility, high purity material. Only issue is that when you oxidize it, it's porous to water and hydrogen. That's a kind of problematic to electronic system. That is why very old electronic system like computers, you have to put them in very clean rooms where there's no water and reduce hydrogen. Right. So with this slide, I will stop today's session.
Recording stopped.
Few things, take home messages. So unless you interact with me, I don't like to do classes. And the assignments that you are, there is a like quiz that I would like if you do it. And also in today itself, after all the sessions, if you can go through these slides and try to understand certain things, that could be wonderful. Otherwise, you might forget them, right? So although this is kind of very boring, so this is basically the physics behind semiconducting materials. So maybe I'll take another half a day to finish this section, and then I'll move to the electronics that you are really interested in. Okay, so with that, I'll stop. So I'll upload the materials. Already last year recording is there, and I'll upload this recording as well. Thank you all.